All right, this is part two of this week's lecture, and I'm sorry I forgot about this. All right, so we're looking at magnetism again and looking at how things react. So let's take a look at how particles moving in a magnetic field. So if we have a charged particle and it's not moving, there's no magnetic force observed. It's in the magnetic field, but for a magnetic pole force on that particle, it has to be moving. And then we get a magnetic force, either one way or the other. Now, with this, as you can see here, it's also the direction of its moving. So if it is moving parallel to the force of the magnetic field, as it's going away, we don't see a force. So it's just kind of like going down. So you're in a car and you're going down a hill, maybe a go-kart or a soapbox derby. Some kids make these little cars that they drive down a hill. And so they do that, and there's no force, so they can just see it go down. There's no force acting on that body. But if you're doing it perpendicular, charged particle goes perpendicular to the magnetic field, they're going to feel a force on them going down. And so in this class, what we're going to do is limit the calculations for that electrical charge moving with perpendicular to the force. So we're going to look at, it's either one of these two. So if it's parallel to the field for magnetic force, it's going to be 0. If it's perpendicular, it's going to feel the full force of the reaction. And you're going to have the highest force on the particle. So if the angle 0 is perpendicular to the field, which is what we want, if it's at 90 degrees, it's parallel to the field, and cosine of 90 is 0. So guess what? That's the two types of situations. And the equation we use to figure out the force acting on that particle is QVB, where Q is charge, V is velocity, and B is the magnetic field, and you see all this stuff. And there's all the units. Make sure the velocity is in meters per second, charge is in coulombs, and is the force newtons, and Tesla, this big T, is equal to newtons divided by coulombs times meter divided by seconds, or newton seconds over coulombs meters. And another way to write that is that T is equal to NS, newtons times seconds, over coulombs times meters. And that's another way to write the unit for Tesla. Now, an interesting result is that we have this charged particle moving in the magnetic field. It's going to get captured by that magnetic field if it's moving slow enough, and it's going to go into a circle. So we have a magnetic field. If we look at the top, the magnetic field is going into my screen. This is what the axis means. And so the electron particle, I'm going to change my pen color. Come on. So electron travels this way through the charged particle, and next thing you know, it's going to be circling in this magnetic field, and it goes round and round and around until the magnetic field changes or something interacts with this charged particle, and it gets sent away. A lot of analytical instruments in chemistry work on this principle, and there's some really funky stuff that happens, and it's cool. So what happens when we have wires? So if we're capturing this electron, and we're having electrons go through a wire, inducing current through a wire, we're actually going to see a force. Here's the current, there's the magnetic field, and the force associated with that is called BIL. That's B is the magnetic field being generated, I is the current, L is the length of the wire, and good old Bill. So for the results, you have two parallel wires going in the same direction, the current going in the same direction. You're going to get the wires going towards each other. So we got these two wires, current's going this way, current's going this way, and the force is going to be attracted this way, and they're going to come together. And actually, if you think about the magnetic field, positive, negative, or north-south, north-south, and you're going to get this attraction between the north and south. If we flip one of these going the other way, north-south, north-south, you see this is where they repel.